we make, it's the angle is hidden into the background. But for 151, we don't hide that angle. So let's take to that next step. Same setup. Let's do somewhat realistic numbers here. Massive A, what do we make? 100 grams. Mass B will make 250 grams. This length right here, L is 0.65, let's do it, 65 centimeters. And, ooh, better yet, mass A is the unknown. We swing it around and we did 20 revolutions. And we time it for the 20 revolutions to be 17.46 seconds. What is the mass of A? Mass B is in equilibrium. We've already done the force diagram for this. So I've got the tension times the cosine of theta that way, the tension times the sine of theta that way. Again, theta is the angle with the horizontal. We have weight of A acting down, which I know is mg. And then for mass B, I have the weight of B acting down, mg, and the tension acting up. So, equations of motion. We have ft cosine theta is equal to, I'm just going to jump straight to the alternate version, that's ma omega squared r. Then we have ft sine theta minus equals mag, and ft is equal to mg. All right, questions how we got this. I know I skipped a bunch of steps right there because we did it yesterday. And well, yesterday we had a v squared over r, and today we talked about the omega squared r. Questions about how we got this? All right. R, we know is L cosine theta. So I have the tension times cosine of theta is equal to ma omega squared L cosine theta. Cosine thetas will go away. The tension I know is equal to the weight of B, so if it's in equilibrium, so I'm going to make that substitution. So I have mbg is equal to ma omega squared L, which is what we derived over there. And I'm trying to figure out what ma is. Ma is equal to, well, that's just the weight divided by acceleration. We just need to figure out what is omega. What is omega? not the time.
2 pi divided by t.
Yeah, divided by the time. I suspect if you had written it down, you would have written it down correctly. Just the wording was off. All right, so I know omega is the angle divided by the time, so that's 2 pi over the time for 1 revolution. Well, what is the time for 1 revolution here?
The time we have divided by 20.
Yes, because we know what 20 revolutions is. We assume it was swung somewhat evenly, and we end up with
0.837.
837,
73.
873 or 837?
873.
One more time.
873.
873. I'll erase it with my hand. 873 seconds. And we end up with an angular speed of
7.2. Meters a second.
not meters.
Centimeters.
What is 2 pi?
Radians.
Yeah, it's 2 pi radians. That's the angle. So radians per second. Now, if you just said per second, 7.2 per second, officially it's not wrong. Just the reason you put radians in there is to just make for clarity's sake. All right, so we have an angular velocity of, angular speed of 7.2 radians per second. And so now we can plug and chug. The mass of A's got to be, then, I have 250 grams. Let's put it in kilograms because we are that cool like that. Times, assuming it's on Earth, divided by omega, 7.2, squared times my length, which was 0.65. .06.
Yeah, 0.03.
0.03.
Kilograms.
Is there another digit?
1.
Anyone else get the same thing? Anyone else get a different answer?
I got 0.07.
That's, yeah.
We got 3 people with 0.07. Is there another number after that?
2 or 3
Three.
actually.
Based on the majority, we'll go with this one. Because I think there were 4 people who got this and just 1 who got that. All right, so 73 grams. Putting it back into the units we had, the mass over there, or 0.073 kilograms. Now, there's certain flaws with this particular lab in the fact that, are you swinging it consistently? And the reason why we swing it 20 times is that just, the more sampling we have, the better the results are, and physical fluctuations become less important. But it'd also be convenient if we tried different masses hanging so that we get different rates, so there will be a graph with this. Good news, there'll be a graph when you do this lab, which will probably be a week from today, or a week from yesterday. Oh, let's find the angle while we're here. What the heck? Well, based upon the first two equations I have over there, I know sine of theta is equal to MAG over, oh sorry, the second and third equation would be a lot easier, over MBG. So the sine of the angle should be the mass of A over the mass of B. And so it's going to be the arc sine, or inverse sine on most of your calculators, of 0.073 divided by 0.25. Degrees.
16.98.
Now, in the 251 version of this lab, they're actually looking at the angle. They figure out what that angle is physically, and then they compare it to the ideal. I'm sorry, the 151 version, we don't do that. Unless you want to. We can add it in. That's a one-person shake your head no. I assume everyone else is in favor of it. So. Questions to hear? Because we're about to look at different rotational motion problems, or centrifugal motion problems. Just something to pump the class up, if it's possible. All right. Now for the famous car going around a curve problem. Woo. And we will go through, I know it's going to be shocking, but we're going to go through the exact same steps we have been, the facades method of solving this. So, setting up the situation, overhead view. I have a car going around a track. Car's velocity at that moment is in that direction. From a side view, the track is banked. Now, that's probably the most common question when we deal with these, especially, it's usually not asked during class, it's usually asked during the test or quiz of what's meant by banked. A banked road is just one that is sloped like this. So you're going around a curve. So the back end of the car would, this is the rear view. Car's going away from us. And then overhead view. So this road is banked at some angle theta. Typically it's banked with dirt, but if you've done the beltway around Charlotte in the southeast corner, when you go from, I think it's 85 to 485, it's on pillars, so there's this big curve like that. All right. What I want to know is, if my radius of curvature here, so if I imagine I've got a circle, and if my radius of curvature is 100 meters, what is that ideal angle so that I don't have to worry about friction? So we're just going to assume no friction to start with, that the car somehow is going this, oh, I have to give a speed of, either I give the angle or the speed, so let me give a speed. Going at, the speed is 30 meters per second. So what is that ideal angle so that I don't have to worry about the car sliding up or down the ramp? All right. First step is what? Yes. What are the forces acting on the car? What would the other be? Not a force. Yeah, there is not an other in this problem. Yeah, if we look at our checklist here, obviously there's no string or rope or anything tethered to it. Normal force, gravitational force are done. We're assuming no friction to start with, so that's out. And there's no force that I threw into the problem, some mysterious force involved. So we have these two forces involved. So we did the force diagram, what's next?
Coordinate axes.
Before the coordinate axes.
Direction of acceleration.
Yes, acceleration is next. What is the direction of acceleration of this car? At that moment in time. It's accelerating upwards.
Or it's going forward. I was looking at the overhead. Yes.
All right, so I had one.
Going in a third dimension on that.
All right, so in the rear view, you're saying the acceleration is into the board? And you say so we got one into the board, one out of the board, one up at that end. Oh, up that way. Anyone else? Another into the board?
Is that saying that the angle is like going that way, right? Like, because you can't draw that.
That the car is going around this curve like this. And we sort of took a snapshot at this point right here, this angle right here, that's theta, as the car is going around the curve at a constant speed.
So I'm changing mine to into the board.
So if it's into the board, there's got to be a force in that direction. What force is in that direction?
There isn't.
Yeah, there isn't. So, it's also not out of the board for the same reason. There's no force out of the board. So that limits I have only two forces acting on the car right here. So the acceleration is either up, down, left, or right.
It's into to the center because it's centripetal.
Yes, exactly. My acceleration is in that direction. It is towards the center of the circle. The most common mistake that I see is people who've been doing so many box on ramp problems is they put the acceleration down at an angle. If that's the acceleration, then that means that the car would be doing its loop not like this, but like this, which would be a crazy road. I would say driving in a circle is also a crazy road too, but you know, people do that for a living. Yes, I know NASCAR and Formula One tracks are not perfect circles. Let's go with it. All right, so we've got our acceleration. Now what's the next step?
Coordinate axis.
Absolutely. So how do you want to do the coordinate system?
Let's do towards the center, I have positive. And we'll do down is positive, J hat.
All right. What's next?
Decomposition.
All right, what do we need to break up?
Normal force.
Yes, we're not breaking up weight this time. So weight still stays as is. We need to break that up, and so let's see if we can draw some sort of diagram here. Like usual, I drew like a 45-degree angle. I have normal force going this way. That's what I'm breaking up into its components. Into components that are parallel or anti-parallel to my axes here. And we, of course, can go for the usual stunning visual effects. I am going to make that bigger. That is a right angle there. And I'm breaking it up into a horizontal and a vertical component. That is a right triangle. And this angle here is theta. So if this angle here is theta, what is this angle? For you geometry fans, two parallel lines cut by transverse, alternate interior angles are congruent. So what is this angle right here then?
Theta pi.
Yep. The complement of theta. So what is this angle right here then?
Theta.
Yeah. Now you get to this situation and suddenly your mind blanks, but your artistic skills are still intact. The alternate way of doing that is to try to draw it somewhat realistically. I don't know what theta is, but I'm going to make theta much smaller than the way I drew it right there. So if I make that theta, and I'm breaking that up, so I'm breaking theta up into its components. I have to the right, assuming it will let me, and up. I have two angles here. I know one of them is going to be theta and one of them is the complement of theta, but this is a skinny angle, that's the skinny angle, so that's going to be theta. So that's the, try to draw it somewhat realistically to solve it. So if this angle up here is theta and my hypotenuse is the normal force, well, this side right here, the one opposite